So my early research after I got here as a faculty member in 1989, my thesis work was in algorithm animation. So a lot of my initial research was in, I think, information visualization broadly, but more specifically in this area of software visualization or algorithm animation. And the idea is to use visuals to help students understand programs, algorithms, debugging, testing, things like that. So I built some early systems called Tango and Polka, that I made available to anyone over the web, and they could be used in introductory courses for teaching. It was interesting back then because no World Wide Web existed, so that wasn't a distribution forum. We put our software out and people could FTP it and download it and use it. And nowadays, these kind of algorithm animations are everywhere on the web. I've kind of lost track of everything. I don't work in that area so much anymore, but they're all over the web. I know lots of different universities use those kind of things. You know, they were running in Java and now they're running in different kind of web technologies.
This research concerns computation visualization and algorithm animation. Here we see two animations built with Xtango, a shell sort and a pairing heap. Xtango helps programmers easily build animations with smooth, continuous motions. Another ongoing project is visualization of parallel programs, as in this animation of parallel particle simulation. We are also examining how 3D representations can be used to depict computations. These two animations illustrate a depth-first search on a non-planar graph and a quicksort algorithm. 3D representations promise to provide opportunities for innovative new views of programs and computations. CHIME is a system to monitor human-computer interaction and analyze the captured data. Here we see CHIME at work, reporting in the black window the user's interactions in the white window. CHIME can be executed locally, as we see here, or remotely from another machine. In this example, we see a user working at one workstation while being monitored at a second workstation. CHIME is collecting information about the interaction with the system, illustrating its remote capabilities. Notice that CHIME is producing graphical reports of the interaction. The interaction data is being processed by an analysis tool which produces statistics, then generates a report and renders it graphically. CHIME is being extended to support additional analysis techniques and to merge CHIME information with video recordings of user interface tests.
My research morphed from this kind of instructional, education-focused visualization into just much more general data visualization and more specifically information visualization. So right now we work on kind of any kind of data. There's data just everywhere and people want to understand it better. They want to use it for benefit. They want to take away insight and knowledge from it. So lately we've been doing lots of fun things like sports data visualization, looking at NFL teams and their draft. I did one on visualizing the best golf courses in America and where they are. I've also had some work on geospatial visualization. So Alex Godwin, one of my students, doing things like looking at 911 call response data or crimes throughout the city of Atlanta. And trying to find geographic patterns and help with anticipating issues and maybe moving resources around to better places.
Yeah, so there's a bunch. I mean, GVU is 25 years old, has had a lot of impacts, and there were certainly visions of the future built into the projects we did at the very beginning. One of the projects, my very first, that I can think of that fits this model is my very first PhD student, Noel Rappin, was interested in how people worked with computational modeling, in particular how students worked with computational modeling, that they would come to understand what does it mean to build a model of something in a computer, but then they would also use it to learn something new. And he built a modeling environment for the object-oriented programming class that I taught at the time, and we used for years after he graduated. He also built one for chemical engineering. In chemical engineering, their concern was that we teach students all of this math on how to do modeling of these pumping systems, things like that, but the kids don't really understand how it maps from the equations to the real world. So Noel's first version of this thing, you would lay out the pump and the various tanks, and you'd have these pipes, and you say you have to get a certain flow rate at this point here. And his system was designed so that you would actually assemble the model of the thing, not just work with the equations, assemble the model, and then you would flip it over. The user interface would do a flipping motion. And on the back side would be all the equations that would model this system. And you'd be looking for particular values to turn to certain values, and then you'd go back over and you adjust the pumps and the pipes and flip it over. And when we first started piloting this system, he asked people, so did it help you understand the equations? And the students actually responded, what equations? We realized that we made it too simplified of a user interface. They didn't see the equations. They saw the particular spots where they needed to get particular numbers or particular values. So he completely changed it so that on the one side still you laid out the pumping system, but on the other side you had drag and drop components that would assemble the equations. And all the values would be calculated for you, but you had to make the equations to figure out what values you wanted. And then he got really tremendous results. The people who used his modeling system came up with much deeper understanding of the equations and what they were there for than people who didn't. And in a real sense, that foreshadows things like the block-based languages that we use today in Scratch. It foreshadows the kinds of ways that we think about computational modeling, computational thinking. What is it that we want everybody to understand about computing? How should they be using computing in their daily lives? And now we talk about even middle school kids and high school kids building models of things on computers, building models of the physical world and coming to understand them better.
Today's scientific researchers often look at large multivariate data from observations, simulations, or experiments. With present tools, they can explore only a few data attributes at a time and may miss important relations between them. Researchers are also restricted to a limited set of ways of visualizing their data, and if they don't find what they need in a set of pre-programmed modules, must write their own. Glyphmaker helps solve these important problems by allowing the user to define the display methods and also to isolate specific data for viewing and analyzing. Glyphmaker consists of several modules written for the Iris Explorer data flow system. The file reader modules convert user data to the Glyphmaker internal data types. Here, a user loads complex results from a molecular dynamics simulation. In the editor module, users assemble glyphs from basic shapes, such as cubes, spheres, or cylinders. A collection of these glyphs will represent the user's data. Each shape in a glyph has many controllable attributes, such as color, transparency, position, rotations, and scale. By grouping two or more glyphs together, the user can also consider relations between them as binding sites. Grouping links shapes together with a hierarchical set of coordinate transformation matrices, and all of them appear as glyph attributes in the binder. Once users design a glyph, they can choose which input variables will control which attributes of the glyphs. This is called binding. The binder module lists all glyph attributes on the left and all the data variables on the right. Simply point and click to bind them together. Note that each attribute and variable have minimum and maximum values listed. During binding, user data is scaled so its minimum and maximum values correspond to those of the glyph attributes. Here, we assign the glyph attribute for color of sphere number 0 to the sodium shear magnitude in the input data set for the molecular dynamics example, and the sodium atom's X, Y, and Z position attributes to the sphere's X, Y, and Z positions. Glyphs bound to user input data can then be displayed and examined as if they were 3D objects. The users can explore further by redefining the glyph, changing the glyph bindings, or both. For example, we could rebind color to temperature and a vector glyph to stress on the sodium atoms. It is very important to realize that any binding is possible. It would be equally valid to bind sphere's z-axis position to sodium atom temperature and sphere's color to sodium atom z-axis position. This would result in a 2D scatter graph display of glyphs, showing temperature versus XY position, with glyph color denoting z-axis value. Using any binding will allow the user to find new and interesting ways to explore multivariate data. After binding is finished, GlyphMaker creates a three-dimensional object that is instanced for each data object, for example atoms or particles, in the input data set. The glyph attributes change according to the changes in the bound data. It is simple to produce an animation by pumping data time steps through the data flow network. Often a densely packed set of glyphs will obscure each other and hide important data. While some systems use cut planes or erasers to cut away obscuring glyphs, these tools may discard important data features. The GlyphMaker conditional box module avoids these problems. Users can define their own conditional tests using any combination of glyph attributes, not just position. Users can then rebind or redefine glyphs that meet this test. For example, here we rebind all glyphs that fall within the conditional region to show the sodium chloride neon impact region more clearly. Its flexibility makes the GlyphMaker system applicable to a wide range of visualization problems. For example, Marilyn Smith of the Georgia Tech Research Institute has done extensive computational fluid dynamics simulations to investigate turbulence on large tilt-rotor aircraft. Investigators found that a hovering tilt-rotor aircraft sometimes re-ingests its own downwash, forming a fountain of backward circulating air that increases noise and wastes engine power. Smith's fountain effect simulations find time sequences of 3D vector and scalar fields that may hold small vortices obscured by large steady-state flows. With GlyphMaker, we can set up compound sphere and vector glyphs with, for example, momentum bound to the vectors, pressure bound to the sphere color, and temperature bound to the vector color. Thus, we can study the correlation between variables and also conditionally isolate localized vorticity so that it is prominently displayed. Extensions that we are now working on will also allow simultaneous binding and display of streamlines, particle traces, and other fluid flow representations, along with the glyphs shown here. A team of physics researchers led by Dr. Hai Peng and Professor Uzi Landmann at Georgia Tech has performed extensive supercomputer simulations of the molecular dynamics of nanocluster collisions. In these images, a 64-molecule sodium chloride crystal is fired at high speed towards a pool of liquid neon cooled near absolute zero and resting on a metal substrate. Removing half the system with the conditional box allows a clear view of the impact region with temperature mapped to color. Simulations of these collisions help us understand the complex interactions that may occur between individual atoms, including stress tensors, potential energy changes, and heating. With GlyphMaker, we can see many of these attributes at once and quickly find unusual correlations. By isolating the impact region and then removing the sodium chloride crystal, we see that the area of high temperature in the neon is localized only below the impact region, a result that is obscured before we remove the sodium chloride crystal. Here we see tensor data bound to vectors and temperature values bound to color, so we can see the relation between force distribution and heating. In the metal substrate below the neon, one clearly sees the arrangement of forces caused by the crystal symmetry. Here, forces directly below the impact region are along planes normal to the metal surface. One could not recognize this complex spatial pattern without a 3D visualization.